Did you, sir? Hi, everyone. Welcome to another session of online causal inference seminar. The format of today's seminar is slightly different. We will be having two seminar speakers, each plan to talk for half an hour. So we're excited to have our first speaker be Philip Fowler from Causal Institute for Technology, talking to us about self-compatibility, evaluating causal discovery without ground truths. And we're also excited to have our second speaker be Bijan Mazaheri from Broad Institute of MIT and Harvard, talking to us about synthetic potential outcomes and the hierarchy of causal identifiability. And today's Q&A will be handled by Dominic. I'll hand it to him.
Thank you, Razi. Well, as usually, please submit questions via Q&A. We will, if it's a clarifying question, we will directly ask the speakers. But if it's a larger question, we will take them at the end of the seminar. Okay. Without further ado, Bijan, whenever you're ready.
Yep. Let me just share my screen. Okay. You guys can see it? All right. Thank you so much for having me. It's I know it's really early for a lot of you in California, so I appreciate you waking up to hear me talk. Today I'm going to be talking about some work that I've done with Caroline Uhler, and as well as her student, who is now a postdoc at CMU, Chandler Squires. Topic's going to be synthetic potential outcomes and causal mixture identifiability. I'm going to be kind of bridging a gap between sort of potential outcome framework, some graphical stuff, as well as mixture models. And I'm aware that probably very few people are familiar with all three of those. So please do not hesitate to stop me and ask some questions.
Sorry to interrupt you. Currently, you have shared the slides in a way that we see both your current slide and the next slide right next to you. I think we see the speaker view and not the... yeah.
Is that better if I...
Yep, move it further out. Yep, perfect.
Okay, so it looks like I have my speaker view, but I've shared the window, but it's showing the speaker. Okay, I don't need hints on the next slide anyway, so we'll just do it this way.
Perfect.
Okay, so first I'm going to kind of talk about mixture models and give a little bit of background about what I'm talking about when I say mixture models. So a mixture model is sort of defined by a latent class. I'm always going to refer to that variable as U, sort of discrete variable, and I'm going to kind of refer to K as the number of latent classes. Then there's going to be some sort of arbitrary distribution on the observed variables. This graph means nothing. I made a random graph. But the key point is that you have K class-specific distributions on the observed variables. So like this probability of all the variables V given U, I have K of those. And the goal of the mixture model is to sort of recover what those class-specific distributions are and often also the probability of each class. And all we get to see is the marginal probability distribution. So we have to kind of take this expectation over U. I use lowercase to sort of denote an assignment. So we kind of sum over this probability U and then the within class probability distribution. So kind of the most known way of doing this is clustering. So the idea with clustering is also, can you see my whole thing, or is there like a camera in front of it as well?
We see the whole thing, I think.
The whole thing. Okay, good. Because I also have my window of people on the right. Okay, so clustering can kind of broadly be thought of as partitioning up the space and then assigning points to a class associated with that partition. And as I've kind of tried to illustrate here, this doesn't always work because there are occasionally points that may belong to, say, the blue cluster. We've got some blue points now in the red partition because they're closer to the red points, even though they belong to the blue class. So, I actually gathered this data from 3 Gaussians, and obviously there's all this overlap. So clustering isn't really able to capture this overlap. So if we want to actually capture the overlap, there's an algebraic approach. So you can imagine we can write down our within class probability distributions according to some parameters. And then we also can list out a bunch of functions of the variables, which I'll call moments. And the hope is that by sort of writing what those functions should be in expectation, using the parameters, so we have some function of the parameters equal to some function of the variables, which I then can gather statistics from, kind of estimate the expectation. I start writing out these equations. I get a system of equations. At a certain point, I have the same number of equations as unobserved parameters. And if we're lucky, we can sort of solve for those parameters. I say if we're lucky because obviously, you might not have a unique solution, or some of these may sort of be redundant. So this is known as the method of moments, dates back to 1930s from Pearson, and it's kind of a great way of tackling this sort of overlapping problem. So the point that I kind of want to get across is that there's kind of two problems here. There's the problem of labeling individual points, which is sort of the coloring of points here. And then there's the problem of identifying the mixtures. So, and they're kind of like nested within each other. So if I can label the classes, I can then estimate the distribution within those class labels, right? But if I identify the mixtures, it doesn't mean that I can go to any particular point and guarantee you it's part of this class. So it's kind of a one-way nesting of complexity here. So why do I care so much about like these overlapping distributions? Well, it's really important to handle overlap when you want to define classes in terms of a relationship between the variables. So here I actually have a mixture of a sort of positive correlation between the horizontal and vertical axis, whatever those variables are, and a negative correlation. And clearly in the center, there's tons of overlap, so clustering approach is not really going to work. And the topic of this talk is actually not just doing mixtures of relationships, but mixtures of causal relationships. So there's going to be an added layer of complexity there that we're going to try to attack. So what do I mean by mixtures of causal relationships? Can kind of emerge for in a few different ways. One is a heterogeneity in treatment. So here I have something like drug quality, maybe the drug dosage, and also the outcome. There may or may not be an arrow here linking those two. But you can imagine that if I sort of have a uniform response to the drug is like really, really well quality controlled. I have just a single homogeneous response for all the people who are using the drug. But if there's a heterogeneous response, that might indicate something like, we had a bad batch or something was heated up too much, and now some people are not responding to the drug and some people are. So it's kind of important for quality control. Another way you can get heterogeneity is in the subject. So you can imagine that we're giving people vaccines and kind of latent within the sort of response to the vaccine is multiple strains. So if we have a heterogeneous, I lost the all purple one, but if it was heterogeneous, you kind of would, and actually, let's say you start to see effectiveness decline, right? So you might have two sort of responses depending on whether it's homogeneous or heterogeneous. If effectiveness of the vaccines is declining and it's homogeneous, you might say, okay, it's time for everyone to get a booster. Whereas if there's a decline in the average effectiveness, but it's heterogeneous, you might say, oh, okay, there's a new strain that's emerged, and we need to develop a new vaccine or an updated version. And the final version, these both kind of like could or could not actually be inducing some sort of confounding. So a more like concrete example of where the heterogeneity is also inducing a confounding is multiple types of bacteria. And then an antibiotic. And then you can imagine based on like what you're sick with, your doctor might choose which antibiotic to give you or what dosage. And in that case, if you have some sort of homogeneous response and say you're not better after using the antibiotic, you might just increase your dosage to make sure you kill all of the bacteria. But if there was a heterogeneous response, you'd be very worried about inducing some sort of superbug that is resistant to the antibiotic, because the subset of the cells of the bacteria that are resistant are now becoming the population. So these are sort of three motivating examples. And I'm going to call this problem mixture of treatment effects, because the idea is that those sort of confounding variables up at the top, they're not observed. They're unobserved, and we want to recover them. So to understand how to do this, we first need to review the fundamental problem of causal inference. So the idea behind causal inference is, we give treatment to a person and they maybe get better, maybe they don't. And there's always kind of this counterfactual of like, if we didn't give them treatment, what would have happened? Maybe they would have not gotten better. And we'll call and these are sometimes called potential outcomes. So the outcome of getting treatment will be like Y1 and Y0. And the problem is that we can only really observe one at a time, right? And we want to compute the treatment effect, which is the difference between the two of potential outcomes. But if I can't observe them both, I can't really compute the difference. So instead, what we need to do is some kind of pairing. So if I have twins, that's great. Maybe we can interpret one of the twins' outcomes as the counterfactual for the other, but we don't always have twins. So usually what we rely on is comparing two groups of people. And so a randomized controlled trial might ensure that those groups themselves are so-called exchangeable through randomization. But again, can't always get a randomized controlled trial. So how do we ensure exchangeability between groups, especially when sort of like every person is unique? And sort of one of the key insights, it's often used in as assumption in the potential outcomes framework, that's often derived from from the DAG and the graphical models perspective, is that you can with a graph define a sort of axis or a subset of variables upon which you can define exchangeability. So you don't need to worry about all possible ways in which individuals can vary. In this case, the red-blue axis is sort of all that matters with respect to the response to treatment. So using that sort of idea, we can sort of do the clustering sort of approach, right? So if we have this, if the people are varying according to that measure of exchangeability, we can pick regions where people are very similar in their covariates and kind of assume that, okay, similar looking people are probably exchangeable. And then within that, I have some people had the treatment, didn't have the treatment, and I can create those exchangeable groups. And this approach is kind of a very commonly used approach for heterogeneous treatment effects. It's called causal forests. It works pretty well, but there's kind of two problems. The first is that this all assumed that we had access to that adjustment set that defined exchangeability. And if you're familiar with Pearl's framework, this sort of structure that I've drawn here that we saw in the previous slides, U is in the adjustment set. So the sort of class, if I'm going to use this as an adjustment set, I need to be sort of collapsing on a single class in a certain region, which means I can't handle overlap of responses, which remember is like the whole problem we're trying to deal with. The second issue is even if it was unconfounded, you again still couldn't get handle overlap, because if you were to say look in the region close to the origin on this graph, you would be averaging over both of the components, not recovering both of them. So the question is, can we do a sort of method of moments to find these causal responses? And so the first naive approach to solving this problem is using tensor methods. The basic idea is, I know that's a lot of math, but I'm just going to try to explain it high level. Basic idea is that if you have three observable variables, additionally independent conditioned on the class, so I've drawn the DAG here. And those variables are sufficiently rich. So here I've kind of, in the theorem, we usually assume that they're discrete and they take on some number of states. So this will take on, V1 will take on N1 states, V2 will take on N2 states, and V3 will take on N3 states. That's kind of why I drew these matrices. Then I basically am able to look at these things called the observable moments, which are the expected values of a triple. So I pick some value I for V1, some value J for V2, and some value L for V3, and I count how many times that triple occurs. And I use that to make an order 3 tensor. And it turns out, I don't want you to worry about the details, but it turns out that you can decompose this tensor into rank 1 tensors. And if you do that, you identify generically with kind of a set of, there's a set of exceptions, but generically you identify these 3, you'll be able to identify these parameters. So the probability of each of the components, and then the sort of within component expectations of those distributions, of those variables. And this was first shown by Kruskal in 1977, but it's kind of given rise to a bunch of approaches known as tensor methods. So a paper in 2009 by Elizabeth Allman kind of showed how to use this for tons of latent variable problems. And kind of more recently, Anima Namkumar and her collaborators showed a bunch of more applications. So we're kind of always looking for these sort of 3 independent variables to apply this method, conditionally independent. So how can we apply it to mixture treatment effects? Well, the first sort of insight is, okay, if we turned one of those variables into a tuple that included the treatment and the outcome, then we could just solve for the within component distributions, and we could get the conditional average treatment effect conditioned on U, just as one of our outputs for this tensor decomposition. You might ask, okay, like, well, what about, maybe I can induce that by conditioning more generally on the graph, on a more general graph, and that's sort of been explored in this paper that I was a co-author on and that we published in Clear. But it's not what I'm going to talk about today, because I want to observe that this is sort of doing too much, like guaranteeing the identifiability of the mixture is redundant here, because I don't actually care about the parameters for V1 and V3. All I care about is the treatment effect. So, I can care less that V3 has an expectation of 5 sometimes and an expectation of 7 other times. It's not really important for me, so I'm sort of spending a lot of sort of my budget of like identifiability trying to make sure that I can recover that when really I like don't care. Another kind of thing that I don't care about is I don't actually care about the expected values of the potential outcomes themselves. I only care about their difference. So these are sort of two inefficiencies that I want to maybe try to get rid of when I'm solving for these mixtures treatment effects. So with that, I'm going to sort of propose our new approach, which I'll call synthetic potential outcomes. We're going to add 2 more arrows. Now, adding arrows here corresponds to loosening restrictions, because really when you have a DAG, it's like it's the independence constraints that you get that sort of restrict the possible distribution. So this is kind of like, I don't want you to think of this like has to be a faithful distribution. It's just like there could be an arrow there. I no longer need to guarantee that conditional independence. So the conditions that I actually need are X being independent from T given U. So that's X is here, T is here. That's sort of why you can basically, and Y independent of Z given T and U. So these are 2 conditions. I like to see it graphically. If you don't care about graphically, then don't worry about where those arrows are. This is just sort of the graph that describes those conditions. So I'm going to put those conditions off on the side because we're going to use them later. And what I want to do, I'm going to just work out the algorithm for the k equals 2 case, just so we can see what's going on. And so what I want to do is sort of write out the vectors of parameters and see how these things are related. So what do we want? We want this expected value of a potential outcome. And that corresponds to an inner product between the probability distribution on U, I'm using U0 here to mean like U equal to 0, interproducted with those conditional expectations conditioned on T, right? Because you kind of have unconfoundedness once you've conditioned on U. So I'm going to put that up in the upper right. And so how are we going to get that? So we're able to observe inner products between this row vector and these column vectors, right? So when I look at what's the expected value of y, what I'm looking at is, again, the marginal distribution. Remember there I was doing a sum. Now I've just made it an inner product. I have the probability distribution on U interproducted with those conditional y's. And I want you to notice that this is kind of almost what I want to get at, because my row vector is my goal row vector, but my column vector is wrong. And I want you to look at what happens when I condition on T. So when I've conditioned on T, there should be a condition in T here. Otherwise, looks like it's right. It's this vector up at the top, right on top of U. I've sort of made that row vector no longer correct, because I've conditioning on T shifted the distribution on those covariates. This is sort of the difference between intervening and conditioning, right? If I'd intervened, I wouldn't have shifted that distribution. But I have gotten the correct column vector, which is this expected y given T and U. So the question is, how can I get access to this inner product? Well, I want you to notice that sort of every vector in this picture has changed except for one of them. So the vector for x has not changed. Why has it not changed? It's because of this condition that I've highlighted in yellow. X is independent from T, conditioned on U. And remember, the vector is the conditioned on U vectors. So it'd be really great if I could somehow use this wonderful property of X to get access to that inner product that I'm hoping to recover. So what I'm going to do is I'm going to turn X into two features. And I'm also going to do the same for Z. And so what do I mean by two features? You can imagine I have X and X squared. If it's a Gaussian, that'll kind of be two different things that vary. I also, this is a detail you don't need to worry about, but I also have access to the all ones vector always, because it's just a constant. So I can also do, if X was a coin flip, I could do sort of an indicator for heads and an indicator for tails, and that would also work. But so I'm going to turn it into two features. Each would have their own column vector. And I'm going to use kind of this very simple fact from linear algebra, which is that I can write that column vector that I want as a linear combination between those two vectors for X. So if I could just find what those coefficients alpha are, then I would be able to sort of express that vector in the unconditioned on T case and get the inner product that I want. How do I find those alphas? Well, I just write some linear equations which I can solve for. So what I'm doing here is I'm matching such second order moments with Z. So I'm saying, okay, if Y is the same as this linear combination between the X's, then it should also have this second order moment with Z1 that matches the linear combination between the second order moments with Z1 and Z2. And this set of conditions, I'm kind of hiding the detail here. This kind of only works if this second condition holds. So that's where that second condition comes from. So if I rearrange these as a matrix equation, I find this matrix here, which is all just observable statistics. Where this is X's and Z's given T. I can find those. They're all expectations. And I can invert it and solve for the alphas. And then the linear combination of those expected values for x1 and x2 will give me access to exactly that expected value of the potential outcome that I want, because those vectors won't change when I uncondition on T. So this is the procedure. We do this for both. We get alphas for the T equals 1 case. We get betas for the T equals 0 case, and then we just look at their difference. And I'm going to simplify this as expectation of R. R is going to be the difference between the potential outcomes, sort of like the response. And I'm going to put gammas as the difference between the alphas and the betas. So identifiability now corresponds to matrix singularity. Can I invert that matrix? And stability now corresponds to sort of the matrix condition number. It's a detail maybe we could talk about later. So this is sort of a method that is, actually, let me check. How am I doing on time? I don't really know if I started at 6 or.
You still have at least, 5,
Yeah.
6 minutes. Yeah.
Okay, so this is a method that we recently discovered kind of had already been shown, but there's this the method in this paper is slightly different. It's using conditional probabilities, so we've actually sort of generalized it, but it turned out, we'll give credit to this paper that beat us by a little bit. But we can push this farther. So let's say that I kind of wanted access to a response, kind of like 2 independent samples of response from the same like latent class. Well, I'm not gonna kind of like I'm gonna get to it later why we're looking for this. So let's just see if we can access this value of expected value of the potential outcome of a potential outcome times an independent response variable. So this corresponds to this inner product where I've done this element-wise product of the vectors. Well, the idea is I can sort of play the same game because I've already computed a way of simulating R on X. So if I had X and Y independent from each other, right now they're not, but I'm going to make it by removing that arrow. So slightly different, slightly more constrained requirement. Then I can get access to the behavior of like X times R, which has been simulated on X. So we kind of do the same process. I'll blaze through this. Lots of linear algebra, but we can solve for. Then we take the difference of those two. So that's why I'm doing y of 1 times r, is because then I do the difference and I end up getting the expected value, the sort of second order moment of the response squared. So why am I like trying to solve that? It turns out there's a problem called k-coins, and I'm going to explain this very quickly just to give some intuition. So I want you to imagine I have 2 pockets. And in one pocket, I have a homogeneous mixture. So I have 2 fair coins. In one pocket, I have one that's biased towards heads and one that's biased towards tail. And so if I only had sort of access to one independent sample, I wouldn't be able to tell the difference between these 2 mixtures, right? So it'd be heads half the time, tails half the time, even though there's kind of 2 different coins. But if I were allowed to flip the coin 2 times after I sort of chose the coin, choosing the coin here is like choosing U, then I would notice, then I would notice that the distribution would sort of bias towards heads, heads, and tails, tails for the heterogeneous response, and will bias towards, will be even for the homogeneous response, right? So this is called the k-coin problem, and it's sort of been solved, again, using method of moments. So I kind of have these, I have 3, let's say, I have 3 different independent samples of the response variable that corresponds to these 3 vectors. And I kind of gather these 3 statistics by iteratively applying that method of synthetic potential outcomes. And you can kind of count the degrees of freedom here. So I have k minus 1 from the distribution on U, because there's k parameters, but they need to sum to 1. And then I have k from the sort of vector of conditionals. So it turns out once I get 2k minus 1 of these moments, which in the k equals 2 cases 3, I can recover my mixture. So that solves the problem. And it's sort of a reduced way of, I mean, this is method of moments, but I'm only focusing on the parameters I'm looking to recover. So in summary, there's sort of this hierarchy of identifiability. We started with heterogeneous treatment effects, which required observed U. Then we observed that there was this sort of mixture model recovery problem, which required no edges. And then if there was an edge from Z to T, we could recover the mixture of treatment effects. And then an edge from X to Y is all that is needed for recovering an average treatment effect. So there's kind of a few points I want to say about this. And this hierarchy is like disjoint, right? So I kind of explained that there's examples where maybe you can identify the level that's being described, but not the levels that are lower down. you can always use the levels, the higher levels to identify the lower levels, but not the other way around. So I can always use mixture treatment effects to identify average treatment effect because I just marginalize, right? So the first point that I think is important to notice is that clustering-like methods, which include IPW and covariate adjustments, are sort of fundamentally limited. And that's sort of explained by that overlapping part that I talked about. The second is that in the absence of sort of validation, we can't really play the game that machine learning people play. So we can't just say, oh, we held out this data and, oh, look, our method is working. So I really think it's important for us to focus on identifiability, because unless we do an experiment, we don't know if we're right unless we sort of guarantee that we're in an identifiable scenario. That kind of goes along with sample complexity. I didn't talk about sample complexity, but you can think of sample complexity in sort of the same way, but instead it's sort of the fuzzy case instead of the absolute case of parameters mapping to statistics. Finally, when we're developing methods, we need to sort of recover solutions at the granularity at which we care about the answers. So if we sort of hit something with a hammer, then we're sort of beholden to the requirements of that hammer. It makes for a nice clean paper, but it might not be as efficient as sort of trying to solve the actual problem at hand. And so this paper is called Synthetic Potential Outcomes and Causal Mixture Identifiability. There's a preprint on arXiv right now, but a new version will be appearing in a few days, hopefully. So I guess email me if you're want to take a look or have any questions. And with that, I want to thank my current collaborators, my PhD collaborators, who kind of a lot of this work kind of came out of some of the stuff I'd done during my PhD. And then also funding. The Eric and Wendy Schmidt Center is a fantastic center at the Broad. We're working on biology problems as motivation for machine learning problems, as well as machine learning problems that solve biology problems. It's been really fun working there. And finally, a very quick plug. I'm going to be starting as a faculty at Dartmouth in January, and I am looking for students. So if any of this interests you, please reach out. Thank you very much. Happy to take questions.
Great. Thanks for the very nice talk. Yeah, again, please submit questions in Q&A. There's one that I currently see there, where we have the question, can this be linked to methods of tensor completion?
So it's kind of a broad question, I guess. In a way, yes, but we need to take advantage of sort of degeneracies in the completing the tensor is maybe something like doing the tensor decomposition. I know that there's synthetic interventions and synthetic controls can sometimes be thought of this. And one way to relate those two is maybe if you think of data as a matrix where each row is an entry. The idea behind a synthetic control is sort of taking advantage of low row rank and finding linear combinations of rows that mimic other linear combinations of rows. We're kind of dealing with columns here. So we're kind of synthetically copying a variable using linear dependencies of the columns. And so row rank, column rank, kind of same thing, right? But what you're able to do is hone in on just recovering a specific column because the column is what you care about, which is the response of that variable y, rather than worrying about finding a group that matches in all the variables that you measured. So I don't know if I fully answered your question, but that's, I think, at least the relationship to the synthetic controls.
So if you have a follow-up question, you can raise your hand, and then we can also unmute you if you want to ask a follow-up question on that. Okay, but I also have a quick question. So am I right that you had to choose the number of mixture components, so the K that you had? How would you do that in practice, or would you just try a bunch and then see whether estimates.
Yeah. So there's kind of ways to see whether K is sufficient. I mean, choosing K is almost always a problem with this. Like K means, like I want to do clustering, how many means, right? So the answer is always some flavor of try different Ks. One thing that's worth noting is that if you do have two variables that are conditionally independent, conditioned on K, this is sort of the relationship to the tensor decomposition part where, so if those variables are independent conditioned on U, then their joint probability distribution is an outer product, which is rank 1, right? And so now I'm doing a sort of, the mixture is sort of a sum of like probability of U times this rank 1 matrix, so I have K elements in that sum. So I usually end up with something like rank K. So if I'm able to have, if I have like rich enough variables, I say rich enough because you need to turn it into, you need to turn your independent variables A and B into like A1 through a K+1, right, to be able to detect this rank degeneracy. And that's going to depend on the parameterization. So like a Gaussian can only be turned into 2 of these features, but maybe. But in general, if I have a rich enough, or maybe I can combine multiple variables, I can look at one of these matrices and say, what's the rank? And that's really kind of what I'm taking advantage of anyway. So yeah, so you can sort of test to see if K is sufficient in that way.
All right. Yeah, thanks. Sounds good. Okay, I currently don't see further questions in Q&A. And I think we're also at time. So Razi, do you want to wrap up? Okay.
Sure thing. Thanks, Philip and Bijan, for the nice talks. So for next week, we will have Oliver Dukes from Ghent University talking to us about non-parametric tests of treatment effect homogeneity for policymakers. And we will have Edward Kennedy from CMU as the discussant. Hope to see you all there.